Uh, I'm Ryuji Yoshida from Riken, Japan. My talk is on intercomparison of Icosahedral climate model on the G8 code ICOMEX project. So this is content of my talk. First, I talked about the introduction of the ICOMEX project. Secondly, I talked indefiniteness of the exascale computing. Thirdly, the contribution of the Japan team, and then I show the preliminary result, and finally I try to make a summary of this talk. The icosahedral grid models for exascalar system simulations, so called as ICOMEX. This is the consortium for the icosahedral grid models development. So our goal is the realization of the most efficient and smartest exascale system simulations. The project period is from October 2011 to 2014. So we have 4 icosahedral grid models. The one is an ICON. This is Japanese model. The main developer is last talk Hirofumi Tomita, and ICON is the new German icosahedral grid model. And the emphasis is already very famous model. This is also the free participant for this consortium. And the dynamical is the newest icosahedral grid model for this consortium. Okay, so now we have the 4 icosahedral grid model. So anyway, so petascale computing is realized. So the next generation will be the exascale computing. However, we don't know what type of the supercomputer will be chosen for the next generation. So like in a card game, we don't know what color is last, so we can't know the. So it is difficult to decide a policy toward the exascale until the machine is realized. But I think it is too late, because the end of the card game, maybe the new generation card game will be start. And so maybe we encounter many roadblocks on the road towards to the exascale era. So for example, in file I/O speed, low byte flops rate, and GPU or many core architectures. So of course, we can find some solutions for these problems. For example, file I/O or domain-specific languages. However, these problems too much for one developing groups. So we are thinking about sharing these problems among our participants. So the key word for this consortium is the synergy effect. Okay. So let's move on to the contribution of the Japanese team. So member is 3 persons. One is Masaki Sato. He is a professor in University Tokyo, and second is Hirofumi Tomita. He is there, and me. Okay. And the project of the Japan team is model intercomparison. So what is different within the model? Of course, all model is based on the icosahedral grid model, but the Nikon is Arakawa A-grid hexagonal structured, but the icon Arakawa C-grid triangle unstructured. For emphasis, Arakawa C-grid, but the hexagonal unstructured. So dynamical is Arakawa C-grid hexagonal but structured. So what causes difference of the result by the result of grid arrangement? Okay. And of course, we want to focus on the computational performance. So what the difference is found between the computer architecture? So we can choose many, we have the many options for CPU architecture, interconnections, and file systems. So what causes the difference of the computational performance by the difference of the computer architectures? So model intercomparison can provide basic information for other groups, both computational aspect and scientific aspect. So, computational aspects including the performance in one node and performance over the nodes. The scientific aspect including the numerical error or the convergence of the computation. And also model intercomparison exploit the synergy effect. So regularly intercomparing the developing model cores on the wide variety of the computer platforms. So this is our plan. The target experiment, deterministic test and statistical test. The Balkanic wave test of Jablonski and Williamson 2006 is selected as a deterministic test, and Hertz-Schwarz and the multi-year arc-planet test is chosen as a statistical test. Now also we are planning about for AMI plan. Okay. So let's move on to the preliminary result. First is a Hertz-Schwarz test case. The used model is NICOM and ICOM. Resolution is about 200 kilometer resolution, and integration period is 1300 days. The first 300 days are for spin-up. And used computational platform is InterGeom Westmere cluster. So this is a donor mean. And the left side is the original paper, and the center is NICOM, and the right side is ICOM. So climate properties of these two models have good agreement with that of the original paper. Comparing NICOM and ICOM, average zonal wind speed is in NICOM is slightly stronger than ICOM, that of ICOM. Okay, this is also the same zonal means figure, but all of them is for NICOM. On the left side is 240 kilometer horizontal resolution, and the center is 120 kilometer, and the right side is 60 kilometer. So the horizontal resolution is different. The maximum of the wind speed at zonal wind speed is lower in high resolution, and wind speed is higher in the low resolution. So, and also the low temperature area at tropics near troposphere is getting intense with increase of the resolution. So we want to check the such resolution dependency on the ICOM model and comparing the among NICOM and ICOM. Okay, and next is Balkanic wave test. The used models are also NICOM and ICOM, and the resolution is about 120 kilometer horizontal resolution, and the integration is 12 days. The used platform is InterGeom Turbo-K. So this is a horizontal temperature at 1.5 kilometer height. In 5 days, we can find the moderate wave, and 7 days the wave is growing, and then the 9th day the wave is almost mature stage. So NICOM and ICOM simulated a similar growth of the Balkanic wave, and this is a pressure field, but this is a pressure deviation field. So we can find the similar result in NICOM and ICOM. However, in this case, the configuration of the initial condition for this test is different from the original paper of the Jablonski paper for NICOM. So we want to change the configuration as soon as possible for NICOM to comparing the directory ICOM and NICOM. And also, in this time, the ICOM model used in this test is a little bit old version. So we want to try to using the upgraded new ICOM model. Okay, next is computational performance. we have the three computational computer platform. The one is Sandy Bridge, and Westmere, and AMD Bulldozer. The CPU is different, but the memory is almost the same. And the operation system and compiler MPL libraries, these are the all completely same environment. And all tests were carried out on one node. And performance were measured by using the bar clinic web test case. And optimization for the Sandy Bridge and the Bulldozer, so AVX and FMA's specialized optimize are not used in this case. So this is the result for the parallel efficiency in one node. So left side is lower resolution, and right side is a higher resolution result. And so gray color line is ideal, and red is icon on Sandy Bridge, and light green is icon on AMD machine, and light blue is icon on into Westmere. Yellow is Nikon on Sandy Bridge, and green on Nikon on AMD, and blue is a Nikon on Westmere. So you can find that both Nikon and Icon have strong scaling and lower resolution cases, so left side. However, in the higher resolution case, Nikon AMD does not save the scaling at the margin of the higher margin of the 10 node processes. So one possibility is a merged core module structure of the AMD Bulldozer. It will increase the number of the hops when a core communication with the other cores. So this is a computational efficiency. So color is same before, and the computational efficiency of Sandy Bridge is the best in both of the models. So this is a comparison with the ideal computer performance of each CPU. So the latitudinal axis is a percentage for comparing with the ideal performance. So we can directly comparing with Sandy Bridge and Westmere's and also AMD's. So we can find that Sandy Bridge is the best in this case. So the efficiency decreases with increasing the number of processes, and this would be a result from the decreasing in the parallel efficiency. On the Sandy Bridge, Nikon is better than Icon. However, Icon is better than Nikon on the AMD Bulldozer architecture. So the aim of computational test is we want to find some hint to the exascale computing. The architectures of the exascale computing would be different from the existing processors, but it may be deviation, a kind of deviation of the extent one. Thus, comparing the computational features of the extent processors helps to adaptation to the exascale computing coming in the future. Of course, we should continue to study about some computational performances, but we could find notion below. For example, the comparing difference of MPI implementations in the two Icon and Nikon models by one node round, we can find not only inter-node communication, but also inter-node communication is very important for get more parallel efficiency. And cache tiling is available on Icon, but not in Nikon. So we can find the cache tiling is how much effect for the getting computational performance is cache tiling. So, and also the comparing characteristics of Nikon and Icon for the core architectures. So we can find that Nikon is good for Sandy Bridge, but the Icon is good for the on the bulldozer. So these are the dependence of core architectures. Okay, that's summary of my talk. The ICOMEX project is a synergy of on the ICOMEX project, we want to synergy effect. The synergy effect is needed to develop icosahedral grid model for adaptation to the exascale computing. Herschel's test case was carried out as a statistical test case using an ICOM and ICOM. And Bakunic wave test was carried out as a deterministic test. And environment for model intercomparison has been completed. So now we are considering how the test case should be set up to obtain the C-level comparing among models. The next try to run MFAS and dynamical on the same platform, which the other participant of this consortium. And also we are trying to now I try to ape test case, and but this is have some difficulty. That is the consistency of the physical process is one of different. Okay, that's all. Thank you very much.
I have a question about the parallel efficiency of the low resolution model and the high resolution model. Can you go back to that slide? I was wondering why the high resolution model have the big the vertical axis number is bigger than the lower resolution. What's the reason for this?
Vertical efficiency is because the number of the processors is increasing, increase in higher resolution. Okay.
Nigel. While you're on that plot, is that really the number of processors on the bottom? 10 processors, 20 processors.
Yeah.
Can you use more processors?
Yeah. Yes. So
this is just one node comparison. So we now future try to the many nodes.
Nigel again?
Yeah. Then coming back to the comparisons, there seemed, to my eyes, some relatively large differences even in the Held-Sparrows case. Is that something you're investigating, or is that not?
Here, this one.
The plots were quite.
Plots for here.
Yeah.
So maybe the question is, how do you know which is right?
Yeah. So we can get if we use a lot of high resolution RAM, and this is a reference solution. But now we just this result. So so maybe future work.
Back to this, once again.